Yeah, I have turned the recording on. Share my screen. Yeah, my screen is visible, right, to everyone? Okay. Yeah, okay. So today we will do another example of greedy algorithm. In the last class, I have done the set cover problem. So today we will cover this problem called, I don't know whether you guys are familiar with this one or not. Point denomination problem. Okay. So anybody knows about, does anybody know what is this one? Okay. So the problem says that suppose you have some coins of different denomination. The number of denominations is fixed, but the number of coins are infinite. Okay. So let's say, so let me give an example. For example, like you can take one, let's say there are like some coins of 1 rupees, 4 rupees, 5, 8, something. Okay. And you want to uh, find out, like, and also there is an integer. Let's say you want to like, this problem is similar. Like when you have a cash, let's say you have given someone to change for change, then what do we do? We like take the smaller values and then we like then we add them such that the total number is up to that integer, right? So these are the, let's say, okay, let me, so coins having values, let's say 1, 4, 5. So these are the value of the coin, that is 1 rupee coin, 4 rupee coin, let's say 4 rupee coin, 5 rupee coin, etc. And we want to count how many coins required to make, let's say 20, 20 is pretty obvious, 22 rupees, or make 22. Okay, so one thing is that the number of coins are infinite. This is the assumption. And obviously, we are interested in finding the minimum number of such coins. Okay. So okay, so you're familiar with coin denomination problem. Yeah. So okay. So then do you know the greedy strategy corresponding to this problem? Or okay, let me just say. So for example, now to make 22, how many coins do we need? Like how many ways can we do that? There are like many ways you can do that. So the like the best possible way, it seems like I can choose 4 coins of value 5, reach 22. We can choose 4 coins of value 5, value 5, and 2 coins of 1. We can do that. There is another way. You can take 5 coins of value 4, then 2 coins of value 2. But that's like the total number of coins is in this case is 6, right? So if we choose 5 coins of value 4 and then 2 coins of value 7, value 1, then total number of coin is like 6. How many? 5, 7. So this is the problem. Okay, so you have some values. You need to some values or some value of the coin, some coins of some denomination, and you want to find the total, and there is an integer, and you want to find that how many number of coins you require to reach such that the total sum of those coins, that sum of the denomination of those coins would be the total the value of the integer. And obviously we are interested in the minimization, so this is a minimization problem. Okay, so I think I can write the input now. So input is or rather coins, different denominations of coins, which is C1, C2, Cn, and an integer, let's say anything, let's say W. So we are interested minimum number of coins required to coins such that the sum of their denomination W. Okay. So this is the problem that we are interested in. It's a minimization problem. So since we are already familiar with the greedy technique, we can design some greedy algorithm for this problem, right? So what uh, what should be the greedy algorithm? It's pretty straightforward. So I think I mean, you can guess also. Yeah, I have just executed the same in here. So the first technique is greedy. Okay, so algorithms, greedy strategy. So if we like we have these coins, so see the input. The inputs are the denomination of the coins. So natural idea is that I will select the maximum value, maximum the coin with maximum denominations. I will keep selecting this maximum denominations until I can. Until like if I choose one more, then it will be like the value will be bigger than the total value, and then I will choose the smaller one. Okay, so this is the greedy strategy. So so to do that, I need to sort the weights, right? To sort the denominations. So first step is sort the denominations in decreasing order. Okay, so from higher to low. Next, start with the or start with the maximum weight or maximum denomination. Repeatedly select the coins till maximum denominations, let's say CM, till W minus CM is greater than 0. Okay, so you want this to be greater than 0. Once done, then repeat the same step for the next points, for the next denominations, for the coins, for the next denominations. Till the total is okay. So what does it mean? Means that let's say you start with let's see through an example. So in this example, say your let me denote this by C. Should look similar with- Okay. Now the first step is that and let's say weight is 22, the same thing. Yes. Wait, total sum may be confusing. And W is 22. So now you need to count. So the first step is that you sort this array. So first I will sort this. And I'll start with the first element. What I do, I'll select this first element. So I see that 5, then again 5, then again 5. This is 4 times, so you can directly write 4 into 5. You can see is 20. So and like 25 minus 2 is negative, so that's why we are choosing the 20. Sorry. Four coins of denomination 5 we choose. Next, after we finish this one, we move on to the next because if you choose one more coin, you can easily see that it's bigger than the total. So we have to move to the next value 4. 4. If you add 4, it's still bigger. So you can directly discard 4. Then you go to 2, and yes, we can add 2. So 2 into 1, that 20 plus 2 into 1, that's 22. So implies one coin of denomination 2. Okay. And then there is no need to go to the next one, but you can reverse. So this is the greedy algorithm. And so the total number of coins we obtained is 5 coins. And you can see that this is the optimal in here. Okay. This is precisely equal to the optimal, which is actually the optimal. It's the optimal solution. So you can check whether it's an optimal solution or not. Okay. So the algorithm seems pretty obvious and very easy. But is it like so the natural question is that can there be a situation where it doesn't work? By the way, okay, I will come to that one after this. So there are situations, actually there are examples where this greedy method, like straightforward approach like this, does not result in an optimal solution. Okay, so how it is? Let's see. Greedy is not always optimal. Okay, so let's see an example of this one. So take this set coin equal to 5. No, oh, okay. So it's the total number of coins. See, there are like 4 coins you need of value 5, I mean denomination 5, and you need 1 coin of denomination 2 to make 22. So the total number of coins you need is 5. So that's why it's equal to 5. So we are counting this one, that how many coins are required and the supply and a number of coins. So you have infinite number of this 1 rupee coin, infinite number of 2 rupee coins, infinite number of 4 rupee coins, infinite number of 5 rupee coins. Okay. So you just have to like take the values and such that you can reach the total sum. Okay. But this pretty is not always gives you the optimal solution. For example, if you take this one with weight, let's say 8, so your greedy algorithm will do what? So if this is my array, I will first sort it, then I will select 5, okay, till I reach 8. So 1 into 5, implying that 1, 5, 1 coin of denomination 5, and after that it will become negative. So I'll shift to the next one. Next one doesn't matter, the last one. So you can see that there is like 3 into 1, 3 coins of denomination 1. Basically, you can write 8 minus 5 equal to 3. So 3 coins of denomination. So I should have 20 minus, so 22 minus 20. This is the thing. Okay, so there is, you need 3 coins of denomination 1. So total number of coins is 4, right? But optimal is 2. 4 plus 4, 2 coins. 4 plus 4 means what I wanted to write is that 2, which is basically 2 coins of denomination 4. Okay, so this is the problem with this method. This doesn't work for every input. But I think you have observed that in our daily life, we actually use this algorithm. Whenever we are giving someone some changes, we try to maximize the value, select the maximum value, whatever available in your uh, uh, with you, and then you first select the big maximum value, then you select the smaller coins such that you can make the whole value. So this is the so this algorithm particularly it actually works for our like the way our monetary systems are designed. So for example, if you have weights, have your or not weights, have you have your denominations of the form like 1, 2, 5, 10, 50, 100, our denomination, this algorithm works. Even this algorithm works for other for some special cases actually, where the so okay, this is an example of our so there greedy works for the like, monetary system, I should say. And also it also works with some other inputs also, and the nature of the inputs are like if they are multiple of each other. Okay, what is the meaning of that? See, you can observe from here that if these weights are multiple of one another, okay, then you can, for example, here, okay, let me just give an example. Okay. So let's say you have this kind of weights. Now you have to reach to some values. Let's say there are for whatever the weight is. See, the available denominations that you have is a multiple of like one another, and also they are like if you take the smaller value, you can just replace the number of smaller values by these bigger values, which are multiple of this one. So in sum, when you sum the values, let's say you have 3 number of 2's, then you can easily replace it with 6. So that's why in this case, greedy will be the greedy choices works. Okay. Am I clear about that? For example, like if you have a weight, take any weight. Take 5 is easy. Take any number, what you want. Let's say 30. Okay. So greedy will do what? So greedy choice will give you 3 coins of denomination 8 and 1 coin of denomination 6. Okay, that would be the greedy choice. And that is precisely the optimal choice in this case also. Okay, so why this works? I mean, why this kind of multiple of one another works is easy to see, because if the coins are multiple of one another, for example, like if you have, let's say, let me do it in more special, more generalized way. Let's say you have these coins C1, C2, Cn, where each Ci and they are ordered. Let's say they are ordered C1 less than C2 less than Cn, and like each Ci is some let's say k multiple of Ci minus 1. Okay. So some multiple of this. Now, if your weight W is some, if your weight is W, you need to get to the weight first. Okay. So how you can reach up to this W? The greedy algorithm says you select the maximum one. Now, you can see that if the maximum one is available in here, then 8 into 4, 8, 4, oh, minus. No, we are not, see, okay. No. See, we are not doing the subtraction in here. Okay, it's like you add, you have some coins. For example, when you do the, when you give someone changes, suppose someone give you 100 rupees for change, to give you some change, or you give someone 100 rupees to give like to receive some changes. So how does he pay? He will, if he has 250s, he will ask you for 250s. Otherwise, he will ask for like 150, 510. The number of like whatever the denomination or the how many number of notes you have with you is depending on that. Right. So we are not like we are not exceeding. This is the same problem. We are just copying that same problem in here. So we don't exceed the value and then we subtract. We wanted to count that how many coins you can ATM changing machine. I don't know whether ATM changing machine. Yes, ATM. Yeah, this is the purpose. That's the changing coin is to just yeah, exactly. How to organize these uh, things. That exact same algorithm is used in I mean, not exact same, maybe some different, but this same type of algorithm is used in this ATM machine. Yes, you are right. And they wanted to count the maximum and then they reach up to the amount that we have entered. Okay, so now you can see that if the weights are multiple of one another, that I'm saying in here. So if you wanted to reach to the weight W, so let's say your maximum weight is CM. Okay, so if W minus CM is positive, okay, you cannot select any smaller weight and any smaller denomination and reach up to W, because if you do, you have this luxury that, okay, I can use this one because it's larger. Okay, it will reach to the value faster because one of them is multiple of other. So for example, like if you don't use this one, then you have to use the other one, like, sorry. So you let's say if you skip CM, you have to use some other smaller values, right? Now you have to come up with this up to CM. Like if you are using some kind of CJ, which is less than CM, and we know that CM is some K times CJ, then you can, like, since W minus CM is greater than 0, so if you are selecting this CJ, okay, then you have to at least select this many to reach W. Okay, so okay, so what's your question? This algorithm, this algorithm is precisely what he wrote. That uh, ATM changing machine. It's an example of this one. So that machine does not work independently, right? It has to operate on some pre-programmed uh, codes. So this is precisely the idea of code. This our monetary system actually supports this greedy strategy. So that's why it is applicable in any other example. Okay. Mm, any other I don't recall right now, but you can think of like uh, you have to assign greedy may not work. I mean, there is a dynamic programming algorithm for this one, which works for every input. But yeah, vending machine is same. It's same. It's whatever you are doing. No. Uh, so except from that, I think he is asking except from this one. Basically, if you can think of this one as a like whenever you have a problem having some weights, okay, and you have to reach to a certain weight. For example, it could be scheduling, not scheduling. It could be like total number of work hours. If you have this many hours of like if you have number of some n number of staffs and they have like particular working hours and you have to like make it up to this many work hours for every employee, then you have to like this kind of example, okay, for every employee, then you can like check that how many employees from each kind you can appoint so that you can reach what is the minimum number of employees that you can appoint such that you can do this task within this hour. Good. So that could be an application of this one you can think of. Okay. Other examples I don't recall right now. Sure. Okay. So you have to keep, so what, where I was, so you have to keep selecting till this CM quantity. So the better choice would be to include CM in there. Okay, so this is why the multiple of, if the weights are multiple of one another, I mean, if the denominations are multiple of one another, then greedy strategy works. Okay, so greedy strategy works. Yeah, the denominations. uh, Multiple of one another. And also if they appear in some series, I mean, multiple of one another means they can be in the form of series. So that's called a canonical form actually. So if I'm writing this one also, so if they're formed of something like this, okay, this is your yeah, it's the monetary system and this system is analogous, right? So you can not like don't need to separate the weight system with this one. Okay. So where was mm, R is the set of denominations where P is equal to 2 quantity. So if your set of denominations looks like this, then the this this coin denomination problem is called its canonical form. And like you can also think of this as a is called canonical. Base system. Okay, so this form is guaranteed that your greedy algorithm will work. Okay. Now, there is also another way to apply the greedy algorithm in here is like divide the weights by the denomination, and then you sort them, and then you apply the greedy strategy. Okay, so these are the ways you can design the greedy algorithm, but it's obvious that this is not the correct or the perfect strategy for this problem. So there is a dynamic programming algorithm to solve this problem. Can you think of a dynamic programming algorithm since you have done this dynamic programming? So can you observe any structure in here? Okay. Can you think of any dynamic programming strategy? I mean, how you can implement this? Yes, I think the problem is clear, right? What we wanted to do. Now, can you design a dynamic programming algorithm? Yes. Okay, the problem is not clear. Okay, so you have a set of denominations of coins. The number of coins are infinite, and value. You have to find the minimum number of coins such that the sum of their denomination is equal to the value. Okay, so this is the problem. So can you come up with a dynamic programming algorithm? Okay, so okay, I'll give you think about it. So you can apply the top-down approach. Both approach you can apply, bottom-up, top-down, both. Uh, can you observe a structure in this problem? What would be the sub-problems? So let's say you have these values. What did I take? And the weight is 8. So you can think of this as a, for example, you have this weight 8, have this weight 8. Now you have this option, choosing a 1 rupee coin. Okay. So if you choose 1 rupee coin, the remaining amount is remaining amount is 7. If you choose the 4 rupee coin, the remaining amount is 4. If you choose the 5 rupee coin, the remaining amount is 3. Okay. Now you can see that, okay, now in this position, I have again 3 choices. I can select 1 rupee coin, which will result in 6. I can select this 4 rupee coin, which will give you 3. And I can select the 5 rupee coin, which will give you 2. Okay. And there here also we have this choice 3. Actually 0. And 5, which is not possible. So negative. I mean, it's not possible. So I just write -1. Okay. Because it's not possible. And similar thing in here also. Okay. So similar thing in here also, you have 1, 4, 5 choice, and for each choices you will have some value. So you can see that, okay, I reached at this step and I got my answer, it's 0. And for every other cases, you have to go down below this level. That means you are selecting more than one element. So that means you don't need to like expand further. Okay, so this means that we can start with a problem. And we can start with a smaller problem, and we can check and we start and what should be the sub problem? It should be that suppose you are at a certain weight, certain denomination, you have to select, I have to choose whether this denomination is in the set or not. Okay, same like dynamic programming. You have to decide whether this is, so you have to take the minimum of both of them. Okay, and that will give you the solution. So you start with your base case is 0 because the value of the denomination when you are starting, there is no coin. So you have if you start with 0 and you assign infinity to every other weights. Okay, and then whenever you add 1, you just update the table. Okay, so it's same. You have to maintain a table and you have to follow. It's a kind of bottom-up technique. So you start with the lower level and then you went up to the total value. Okay. So this is the dynamic programming algorithm. I am not discussing it thoroughly in here. I just write that this problem can be solved optimally using dynamic programming. Okay. And I just mentioned the sub problems. You can figure out the recursions from here. So at each step, decide whether the while processing a denomination, we decide whether we select the denomination or not. Okay. So this is precisely the sub problems that we deal with. This is a bottom-up approach. And maintainable. And you can write the recursions as if the ith coin is processing, then you will select so it's either the same or the same. Uh, so either you add the coin and subtract the total from there, or you just apply the recursion. Okay. Okay. So try to write the this try to like design this dynamic programming algorithm for this problem. uh, based on this recursion. You can go, you can like apply. You can go for bottom up, top down approach also. That also works. Okay, so dynamic programming actually results in the optimal solution for this problem. Anyway, okay. Okay, so any questions regarding this? Okay. So if there is right, so if there is no question, then I'm shifting to bottom-up approach is like in the dynamic programming, while designing the dynamic programming algorithms, you there are two ways. Okay, so you have like you have the original problem, and then you look into the sub problem. That's the basic idea, and you solve them through recursion, but you store the value. Okay. Uh, what this bottom up technique is that you start with the lower level sub problem, and then you gradually solve the problems up to the till you reach the original problem. That's your bottom up approach, and you maintain a table for the recursions. That's called the table will be filled from down to top. That's your tabulization. That's called tabulization. That's the table for dynamic program. And whenever you are writing the top-down approach, okay, you are starting with the original problem, and you break, and you solve the and you break the problems into smaller sub-problems, and then you solve these sub-problems. You store these sub-problems in a solution. It's called memoization, and then you in a table. It's again a table. That's called memoization, and then you again use that table whenever you are calling the further recursions. Is it clear or? Okay, so I'm moving to the coding part. So today we will do the coding for these two problems, Hoffman coding and job scheduling. I think job scheduling problem was covered in your class, in the last class, right? Okay, so since Hoffman coding is done in your class, I want to know whether uh, you have done this called binary tree. Do you have any idea about binary tree or heap? Is a heap sort algorithm is covered in your class? Okay. Difficult. The heap sort is not covered. Okay. Binary tree. Do you have any idea about binary trees? Or any tree? Tree, you do know what is a tree? Okay, okay, okay. So for today's code, actually, I think if you have done Hoffman coding, then you already know that you require this heap sort or like min heap, minimum heap. That's not heap sort. Uh, you have to build a min heap to implement this Hoffman coding. So that's why I was asking that whether you guys can do this thing or not. Okay, fine. Then I'm shifting to this coding part. Okay, so to write this code first, we will solve this job scheduling problem. Okay. Uh, So I hope all of you remember the algorithm. Okay. What was the algorithm for this? The greedy algorithm. We will solve this problem using greedy strategy. The problem was to, like, you have some jobs with certain weights, and you have to with given weights, and it's completion time actually. You have to schedule them such that the jobs will uh, hmm, so the job with the um, that you can finish the jobs according to their completion time. So what is the like, okay, so for this, to code this one in here, we require I don't know whether you are familiar with this called structures in C. So structures in C are basically we this struct variable, we use this struct which actually help to group some different type of variables. It can be same, but it can help to like group different type of variables altogether. Okay. Uh, so we will be like, we need this structure because there are two things in here. One is the weight of the job, and its time. So we will be doing those. Okay. Cost and I mean actually cost, whatever. I think it was cost. Sorry, is cost, I guess. So screen not visible. Oh, okay, okay. So the structure is a very important feature actually. We will use this for different purposes. Like uh, we can like we'll be needing this when we are dealing with those algorithms involving binary tree, uh, other these graph algorithms. Okay, whenever there is a node type things that you have to use, we will be using this structure. Okay. Uh, for this, and also like our purpose, because you know that I think you recall that you need to sort the jobs according to their priorities, right? You have to sort the jobs according to the ratio, and then you select the maximum ratio job to be finished first. So that's the job scheduling. So your this ratio, the weight ratio, the greedy ratio that we have covered, that I think covered in your class, it's so it requires like, so each job has two features. One is the cost, another is the weight. So that's what I will. So to incorporate those two things in here, we have to use this structure where we can assign these two things with the job. Okay. So, and also you need to sort, as I told you already. So I will be using a function directly. You can, oh, sorry, you can use, or you can, it's better if you write any sorting algorithm, but there are like quick sort can be implemented directly in C using this qsort command, which has arguments like the in the argument of qsort, you just pass the array that need to be sorted, the number of elements, and also the function over which you want, like comparison function, like what should be the comparison between the two things. So here we actually use these two things. First, we construct a structure, then we define a function which actually define how we compare two jobs by their ratios, and then we directly goes to the main function. Directly go to the main function. We are not calling any function anymore. We directly go to the main function, and then we directly type this. Okay. Okay. So first thing is the structure. So a job has an number. So that's this job ID. And we define this variable. It's the cost, and this is the weight. And also you have to ratio. Okay. So the way to define structure is that you this is the name of the variable, right? And then we in the second bracket we write whatever the variables that we wanted to define in here, and then then it comes the name of the structure, name of the variable, actually the structure variable, which is job in this case. Okay. Okay. Give me a 1 minute. Um, just 2 minutes. Okay. Am I audible? Yeah. So, hello, am I audible? Okay. So, any questions like what is this structure? Screen not shared. Okay, it's open, right? Yeah. Okay. So, any questions regarding this structure uh, variable? Type def is we use when we uh, see we are declaring this variable outside of any functions and uh, like we are not using this we are not directly defining this variable structure in some functions, right? We are declaring this before calling anything. So type def is basically it gives you the freedom to like define any variable you want. Okay, it's basically any variable of your type. Okay, it's kind of declaring some variables. So this type def is just to declare the variable. If you are using some uh, functions and then you are declaring the variable inside the functions, which are uh, so in that case, you don't need to define this type def, but generally this type def is to define the variables. Okay. And job is the name of that variable. See, the structure is the type of the variable, the data type. Okay, and the name of the variable should have a name, and that name is job. So it actually, for this structure, it creates a name like whenever we are declaring, let's say, some variables like integer I. So this is basically what the type diff is doing. So it's giving a new name to this structure, which is job in here. Okay, so this is the way we use the structure in here. Next, we define a function which will compare two jobs based on their weight ratios. Okay. I'm telling you what are the arguments are. Just let me write this one first. Oh, I think I have discussed about pointers and how to access a value in the pointer, right? So this arrow means we are accessing the value that's stored in that location. A is the pointer. Okay. Its type is structure, and we are so when we are calling the value of A, we are actually referring to the ratio, value of the ratio. Okay. So this is basically the comparison of the two ratios. Okay. So for the two jobs, if this okay, so this will and if the other way around. So about this function, what does it do? It's actually we are okay. Are you familiar with this variable constant? Hmm. And why are we using this constant? Fixed value, yes. It's and this constant void pointer. What? So it means that the value it's pointing at is a fixed value. It's not going to change. Solve the program. Okay. So this is the meaning of defining these variables. And here we are corresponding to each jobs. We define two pointers and each pointer is accessing the ratio. See, this job is a structure in here. Okay. So this const job, I mean this const job is basically is calling the structure in here, and whenever we are trying to access this and when we are comparing, this a pointer is accessing the value stored in the ratio. Okay. 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 So if so what we want to store, we want to store them in a decreasing order, right? So if the value is in decreasing order, I mean, if the job that you find is the ratio is bigger than the is smaller than the ratio, then we put that job. Then we say that okay, this is what we wanted. Okay, so this is basically a defining a less than order in the jobs. Okay, and the same thing will be done through the sorting. When we do the quick sort, this is the comparison that we are going to use. Okay, this function will be called in quick sort. There is a quick sort uh, shortcut. I mean, it's actually a shortcut. Since writing quick sort again in here would be a like it's a waste of time actually. So that's why I'm avoiding this quick sort. I'm directly using this one. But it's like better to define the sorting function and then use it anyway. So let's continue with this one. Any question in this function? Okay, so now we directly go to the main function. So this n is the number of jobs that we have. Okay. Now we take the input of this. And this job is the name of the variable, like integer. This is the name that we have given to this structure job. Okay, so I'm now calling this function, this structure variable. So this job is corresponding to the structure one. Okay. And similarly, like we are using the dynamic memory allocation. So malloc size. Now it's to take the inputs for each job. Yeah, for now. Okay. Now this thing that you see is what we use when we are calling a function. And see here, this job is a pointer. Okay, this is the type of the variable, and this is the pointer. Okay, uh, we rename this structure as this job, start variable as job, and we are whenever we are using this, we are using this job, and this is a pointer, and that's why we are using this arrow to access to the value. Now we are accessing to this each job has this ID, and since we have defined this job as a structure variable, so our structure variable has these components. So each of them has these components. To access those components, you have to use this format, like it's dot. Uh, it's the is the is the type that you wanted to, hmm, uh, and their corresponding like ID. Okay. And the corresponding variable that you wanted to access. If you wanted to access ID, if you wanted to access ratio, it will be ratio. So it's in this way. Okay. So ID will be just the number of jobs. We can give them like job 1, job 2 to job n. So that's why I'm assigning job n plus 1, I plus 1. And now I am putting the value p, and store the value of w. and store the value of ratio. So, oh, ratio is what? W by P. Okay, so now we have taken input for this array. Each element of this array is defined as the, I mean, you have the structure, you have this, have each values for each of these components. Now you want to sort these jobs. Okay, so this Q sort is the direct command that uses this quick sort, and it comes under the standard library. Otherwise, it stdlib dot h that we have used. Otherwise, it will not work. Okay, so so the input to this problem is the array that we want to sort. That's job size and the size of the variable. And the function. So now so it's just check if it is n-1, then we go to the new line. Otherwise, keep it back. Okay. So there is any error. And we use malloc so to free the memory. So for the input, you can say like there are 5 jobs, and it would be like the job cost and the value. So say this is for job one. This is for oh sorry. I should print all the jobs. Yeah. So you can check. I think the jobs are arranged according to their weight. Yeah. Okay. So this is the algorithm. I mean, this is the code corresponding to C. The use of this structure is a new thing that we will follow from now. Okay. So any question in this code? Okay. So if there is no question, then I'm going to paste this one. Okay, next is the Hoffman code. Mm. So for this, actually, what we need is the heap. It's a data structure. What? So any data structure covered in your class, like linked list, queue, arrays, we all know, but rather data structures like linked list, stack, queue, mm, binary tree. This is not covered in your class, or you already know. Okay, so you guys know this thing, right? Okay. So do you know heap then? So do you know heap? Heap is a data structure actually. That's why I'm asking. You know heap? Okay, so you know heap. Okay. So what is heap? Ordering, yes. You have to like the min heap is basically the root. You have to you are like organizing the whole elements in a tree-like structure, and the root will return the minimum if it is minimum heap, or if it is maximum heap, then the root will return the maximum, right? And it also maintains the yes. Yes. It's a binary tree also. Hmm. So this heap structure is required because in Hoffman coding, I think you know that the like you need to find the minimum since you are repeatedly. So you have to find the minimum. So we will be dealing with this mean heap. Okay, so now we again define another variable, the structure. Okay, so we name this. So we directly use it. Okay. So this for mean heap we need. So as I have as I have told you before that we need this structure to create nodes. So if you recall that heap or whenever you are doing some tree-like structure, there are nodes, like one node that pointing to other. So this structure will help to create these nodes. So it's a binary tree. That means it has two pointers, one to its left child, another to its right child. Okay, and also it has to have a like. If you look at the heap node, it's a root node, so it will have like two properties. One is it pointing towards the left child and the right child. Yeah, so you know the value, and you repeatedly use this to create a heap-like structure. Okay, and okay, all right. So let me start typing. Of code. Same like previously. Okay. Uh, Now we define this heap node. Okay. It has so if you recall, we are dealing with the characters in Hopman code. So the data type is input characters. And the input is character, so we are using character, and we don't know the frequency. So and then it's always a positive one. So positive or zero. So we use this unsigned, which is corresponding to the positive values. Okay, and it also need a pointer to the left and to the right. So this is the variable that we have defined. Next we again define the nodes for this minimum heap. It's actually C. Okay, so this is basically C. If you look at a node, it stores a pointer to its left or right and some data. Okay, and the frequency that how many uh, times it's uh, that character is occurring. Okay. So defining this one, we will be actually using this node property. Again, size will be positive, so I think the unsigned. So that's the capacity of the minimum heap. And now I'm calling this min heap node. So now we write a function which actually creates new node for this min heap. Same, we are creating an array. Dynamic memory allocation. I think I discussed about this null pointer also. So it's just I'm defining the nodes. Function will return. Okay. So this is the function to return to create nodes. Now we write a function to create a min heap with a certain capacity. Okay. Currently, before building the tree, the size when you put the 0, so that's what we are visualizing here. So this function create a enum heap of given capacity. Now, okay, now we have to uh, if you know how the heapify actually works, it is that you swap the nodes if like whenever a new entry comes, it finds its position by swapping the nodes. So that's why we also define one function which is actually swap to min heap nodes, and this is the function. And this also. Sure. Okay, so this is the swap algorithm that we know. Actually, it's just the pointer execution. Now we are ready to write the hippify function. It's actually minimum heap. So those who don't know about this heap, it will be, I think, difficult for you to understand this one. It's, I mean, how? Uh, this values that the left node is like if you are at a certain node I, it's left. It's actually the property of this binary tree that we will use now. Those who forget binary tree, repeat once. I think you will get this one. So this is just to adjust the positions. Okay. Now, it's just to check the size of the heap, whether it's one or not. Uh, Now we write a function to extract the minimum value. Um, minimum value not from this heap. Okay. Now we write a function which actually inserts new node in heap. uh, write a function which will actually build the heap. It's a very long code. Reducing the values. Sorry. Now we write a function which actually detects whether it's a leaf or not, a node is leaf or not. Now we write a function which actually builds the Huffman tree. And there are two arguments in that function. So we use a value for this. The following code will print the Huffman code from root to the leaf. Almost done. Now the main function. Whatever input you want, you can give. I'm leaving it blank. Just, just nothing. And whatever frequency you wanna give, sign. Okay. And then you just okay. So this is the code. You can put the inputs and check later maybe, and tell me if in the next class, tell me if there is any like mistakes in there or not. Okay, it's a very long code. Okay, so this is it for today. We will meet you in the next class. Okay, thank you everyone. Now I'm closing the meeting.